Motors and generators. Motors used in the municipal arena, inevitably AC current. By far, the significant motor in industry is an AC induction motor. We're just starting to see the beginning of permanent magnet motors um, because of their being used so often in electric vehicles. They are more efficient, just starting to show up. The interesting thing that a induction motor or permanent magnet motor, and you actually see both in some cars, the use of both motors, both induction and permanent magnet, one on one axle, one on the other, for reasons. Um, Basically, because the induction motor can handle more horsepower. Um, the stators are virtually identical. So let's take the stator being stator for stationary, being the outside part of the motor, the rotor being the inside part that actually turns. And what makes an AC uh, induction motor work is Faraday's law about magnetic field operating with a conductor. Okay. Now the stator itself, and this is a three-phase, two-pole. You basically, if you take a phase one, two different poles, phase two, two different poles, phase three, and what that means is you end up as the power is coming in at 60 cycles and changing. If you take a look at this thing, for example, anything above the line will give you a negative magnet. Below the line will give you, not negative, north. Below that line will give you south. So if you take a look at it, uh, first off, A above the line is giving you north, and then it's B that's above the line, and that's giving you north, and then it's C that above the line, and that's giving you the north, okay? So you end up with a rotating field, in this case counterclockwise. And a couple of interesting comment. If you took a compass, tough compass, and put it inside that magnetic field, it would go around and around and around at 3,600 RPM counterclockwise. Now, that magnetic field that's created is not only in the motor, but some of it is outside the motor. And had a case where a service fellow of ours, back before they actually had credit cards that use little radio pinging, straight magnetic strip, and about every other month he had to get a new Visa card, and finally figured out what it was is he's leaning against 100 horse motors while they're running, and of course the magnetic field on the outside of the motor is busy wiping out the credit card. Now, synchronous speed, the speed of the stator rotating magnetic field. Okay, frequency, number of poles go into this equation, 60 hertz in our case, so 7,200 on the top divided by the number of poles. For example, a 6-pole motor, 7,200 divided by 6 would give you 1,200 RPM. Now, as we'll find out in a minute, the actual rotor speed depends on induction. A permanent magnet motor, no. And we'll get to that further. Basically, induction motor always runs a little bit slower than what the synchronous speed is. Permanent motor will be at the synchronous speed. Now, for example, you can see in the three of these, if you've got two poles, 3,600 RPM, the magnetic fields are rotating at 3,600 RPM. 4-pole, they're rotating at 1,800. 6-pole, they're rotating at 1,200. And so a 2-pole synchronous speed is 3,600. 4-pole, you can follow. It goes beyond 12-pole if you really want, but that's about as far as we normally would see it go. By far the most common speed in industry is the 4-pole motor, 1,800 RPM synchronous. Now, induction motor. Faraday's law says you will generate currents within the bars of a rotor or anything, provided there is some difference in speed. And in turn, the current that has been induced within the rotor bars will then create within the rotor a magnetic field. And since you've got a magnetic field outside that's turning and a magnetic field inside, the two either retract or repel at different spots, and the rotor tries to match what the stator's doing. But it can't get all the way, because if the rotor was turning at the same speed as the magnetic field, it wouldn't really be able to generate any power because there's nothing moving past that bar. In other words, the bar is not actually moving relative to the magnetic field. And as rotor speed becomes slower, the magnetic field power input increases. So typical motor about 5% slip, but it varies manufacturer to manufacturer and design. Let's take a look at that further. There's your rotor, there's your stator. Now, when you first go to start the motor, let's say it's an 1800 RPM motor. The field within the stator is turning at 1800 RPM. If the rotor goes in and the rotor is not moving, either it's locked somehow or starting sheer emotion or inertia stops for a moment, the magnetic field's going around, so there's a lot being induced within the bars of the rotor bars of the stator, pardon me, the rotor, and there's a lot of power being developed, which means first off, you're getting as much torque as you can get pretty much, and it's drawing that magnetic field from the stator, so the current is very high. And you really can't sustain that for too long because everything's starting to get hot. Now, as the thing picks up, as the rotor picks up, you eventually get to a point where it's running a bit slower than what the stator magnetic fields are. And at that point, you're getting the horsepower you're looking for. It's designed to run continuously under those conditions. And here's just another way of showing. To say magnetic fields going around the stator are introducing currents within the rotor, and those currents are being used to generate magnetic forces on the rotor, and the action between the stator and rotor magnetic field is what causes the motor to turn. And by the way, with the three-phase motor, if you want it to rotate the other way, all you have to do is cross any two of the leads. Magic. In fact, a lot of people, when they first go to start a motor, don't worry about rotation, just see which way it's going, and then just cross two leads if they don't like the direction it's going. And motors get bigger. This is a motor that actually, the stator of it is being put together vertically, and you can see, pardon me, rotor. This is the rotor, not the stator. I apologize. Imagine how big the stator is for this thing. But there's the rotor, and they're putting on the laminations. There's the bars that go up and down, and it's a pretty big motor. This is a real good little drawing here because you can see, again, a four-pole motor, and it's turning clockwise. The magnetic field is going around, but if you look at it, you'll notice that, just keep your eyes within one of the field, you notice that the stator is running a little bit slower. It has to in order to generate power on those rotor bars, which generates a magnetic force. So that's why you have slippage. Three-phase motor, no problem. It is a rotating field. The problem when you get to single phase is there's nothing to cause it rotating. In other words, basically you've got windings that are opposed on either side of each other, and it's either one is north and the other is north or whatever, top and bottom. There's nothing to tell the rotor which way to go. Sometimes you get lucky and the magnetic field will give it a bit of a kick and the thing will go one direction or the other. You never quite know which. One of the tricks or it'll sit there and buzz. If it's buzzing, one of the tricks you can do on a small one is go over and just grab it and turn it by hand quickly the direction you want. It'll catch it. Now it knows which way to go, and it'll start running. It's like a toy steam engine. You have to tell it which way to go by flipping it. So what you end up doing is putting in a start winding and then using capacitors to delay the power so that first, like at the top, first the very top one is being energized. Then with a slight delay, the one to the right is being energized, and then go the other direction, and that gives us rotation clockwise. And we do that by powering those two start windings, as they're called on the side, with a very large capacitor, a start capacitor. Because it is so large, we actually turn it off with a start switch. As the power drops off and everything else, the start switch will disconnect that start capacitor. They're designed for fairly short life. You leave them on, they will burn themselves out. But when it flips off, very often, not always, but very often, like typical table saw motor, it's only a start capacitor, and the start switch is centrifugal. But in this case, very often they'll put in a run capacitor, which is a continuous use capacitor, and it really is done to improve the performance of the motor. So the start windings still do something after the motor has come up to speed. Single phase motors we're talking about have very poor starting torque. They really are not good at starting, so watch out. And of course, they require the capacitors and switch. Three-phase motors are simple, and as I mentioned, swap any two leads, and a three-phase motor will go the other direction. Induction motor will provide a braking force and generate power if the driven load exceeds the speed of the magnetic field. In other words, let's say you've got an 1800 RPM motor that is running at 17, because the slippage you need is running at 1750 RPM. If you pick that rotor up and power it, like with a turbine or something, power it up to 1850, the thing will then play generator, and instead of having to put power into the stator windings, you get power off the stator windings. And a nice little characteristic, if line power disappears, the thing just quits, just like a motor, just quits doing anything at all. So it's a good safety thing, meaning once it's isolated, no power is generated. Because of the fact that a induction motor will briefly play generator when it's disconnected from power, a temp restart of a induction motor should be delayed a few seconds to allow that magnetic field to decay and avoid serious out-of-phase power conflicts. Some, not all, a lot of adjustable speed drives are actually set up that they can immediately restart into a spinning motor. Now, credit for all this good stuff, induction motor, goes back to Nikola Tesla. He's generally credited with inventing that. Thomas Edison and the DC boys said, no, there's not. That's one of the problems with AC current. You can't have a motor. Well, dear old Tesla, with some help, basically proved in 1888 that that is wrong. You can have an AC current motor, the induction motor. Now, interesting about Tesla, your history lesson for today. He died alone in room 3327 of the New Yorker Hotel on January 7, 1943, at age 86. He had a sign, "Do not disturb," on his room, so it was only several days later that a maid ignored that, and 2 days later, after he placed it, walked in to find him dead. Westinghouse, who'd made millions of dollars off him, were nice enough to, they'd been paying his hotel bill, and they're nice enough to pay his funeral bills. Now, the fact that a rotating magnetic field within a coil will, same concept, induce a voltage in the coils of the stator, that's the principle of an AC alternator or AC generator. The same in AC, virtually same thing. Okay? Now, synchronous motors, which is what permanent magnet motors are. With a permanent magnet, you don't have to worry about generating the magnetic fields within the rotor. They are using permanent magnets to do it. Okay? So if you look at this drawing, the little black things are the permanent magnets stuck on the rotor, and the stator outside is essentially identical to what you would get with an induction motor. And again, same concept as the induction motor, except it's set to go, so to speak. The magnetism is always there. Now, maximum torque is when the magnetic fields are at 90-degree angles from each other. But basically, there it is. When the motor is operating, it rotates at the same speed as what the field does. The difference between them, induction motor and permanent magnet motors, how they do it. In induction motor, you're inducing power in the rotor, which then creates magnets. because there's electromagnets as part of the deal. Permanent magnet, you're using mounted surface permanent magnets. Financial induction motors are cheaper. Permanent motors are higher efficiency, but they operate both the same way. And adjustable speed drives work just fine with permanent magnet motors. Now we know how basically a motor works. Let's get into a little more of the details of motors in general. And motors come in different enclosures. And in terms of dry motors, in other words, non-submersible, there's several different ways of doing it. The most common is what they call open drip proof. In other words, the enclosure is designed to keep people's fingers out of it, getting shocked or whatever, and provide protection from dripping up to 15 degrees from vertical. While often installed outdoors, they're really not intended to be installed outdoors. And we need cooling air for these things. It helps a lot. So we have a centrifugal fan at each end of the motor. So air will come in from the ends and be blowing out the side. You see the side louvers on the thing. And as the motor spins, so does the fan. Now, upgrading that, we get into weather-protected Type 1, specifically designed for installation outdoors. They can be used indoors, and very often are, but they are weatherproof. Seen on vertical turbine pumps. The basic, simplest motor enclosure of the vertical turbine motor, pump motor, is weather-protected 1. There are also Type 2s, which have additional protection for harsh weather environments, okay? Next come TEFC, total enclosed fan cooled. And if you look at the cutaway, while the original fan is still there and spinning, moving air within, it's really just moving it a bit. The real cooling fan is at the end, the back end opposite the output shaft, or in other words, on the right with the green motor there. And the motor is enclosed completely. There's no air going in or out of the motor itself. The fan outside is blowing over the fins of the motor enclosure. They're suitable for environments having dirty air. You see them an awful lot in industry. That's pretty much the standard for industry. Now, an interesting motor is appreciate that if you take I'll go back slightly. Okay. If you take a look at the fan, that fan is tied to the motor speed, of course. And if the motor slows down, then the fan slows down. Now, on a centrifugal pump, that's not a big deal because the power varies as the cube of RPM. So as the motor slows down, the load on it, the motor driving the pump, slows down. The pump load falls way off. So that little bit of cooling is just fine. You can run with a centrifugal pump, run at whatever speed you feel happy with continuously on a drive. They will be happy. I know you hear stories, but no, they won't. Where it poses a problem is if you're driving something where it's constant torque or close to it. In other words, not a centrifugal pump, a positive displacement, which is basically what an Archimedes screw pump is. And I mentioned, as we were talking before, need to be appropriately powered for the highest anticipated inlet liquid depth. Now, because you want cooling because the motor is going to stay quite hot because the load is quite high, what you do is you have a separate constant speed fan motor. And you look at the back of that motor, there's a little tiny smaller motor which is driving the fan only, giving you constant ventilation. Next enclosure, and last one we're going to talk about, is explosion proof. Similar to TEFC, but again, they're built rugged so that if there is an explosion, if gases get into the motor somehow, even though they're enclosed, if they get in somehow and a short or whatever triggers them and there's an explosion inside, it will not be conveyed into the room itself and blow up the room. And they're rated again for the class 1 gases is the most common. You can get them again for fibers and all that good stuff. And group C and D covering methane and hydrogen. So explosion-proof atmospheres, class 1 group C and D is the most common approach. Now, talking horizontal motors, And the expression horizontal applies to a foot-mounted horizontal type motor, regardless of the mounting position. In other words, it may be intended for being mounted horizontal, but if it's mounted vertically, it's still considered a horizontal motor. Sounds slightly crazy. Uh, and you can get different flanges on the end of the motor so that you can be mounted vertically or horizontally to a piece of equipment. Um, and there's JM and JP. What those are, basically like a close coupled pump, centrifugal pump. We talked about that, and the shafts are set up so you can have either mechanical seal or packing. The mechanical seal shaft is quite a bit shorter because mechanical seals are fairly compact, which means less deflection because of the radial thrust of the pump. JPs are much longer because packing is much longer, but you can get motors with those shafts on. It's an industry standard. But all horizontal motors, even if they're mounted vertically with flanges, basically relatively low axial thrust ratings. They can't be used with a vertical turbine pump. And to permit interchangeability, electric motors are built to either NEMA or EMAC in Canada, standardized basic dimensions, so that you can interchange one motor with another. You've got whatever you're powering with a horizontal motor from one manufacturer, and that motor goes up in flames. You're looking around for basically a motor, same enclosure, same horsepower, same speed, and you get it from a different manufacturer. Because they're standardized, it will interchange. The shaft diameter, everything, they will interchange, and away you go. Pardon me. Now, frames. 3600, and it varies with the horsepower, but here's a 30 horse open drip proof motor. At 3600 RPM, it's a frame 284 TS. The S stands for short shaft. That means basically that you can't have a whole lot of radial load, like belts, for example. There isn't enough shaft there to permit you to put a belt on. From there on into standard, 1800 RPM, it's a 286 frame, 1200, 320/16. You can see how the frames get larger and larger because the motor is bigger, because the horsepower the motor has to put out more torque, because horsepower is a combination of torque and RPM. The RPM's going down, so the torque has to go up, which means the motor size has to go up, and the frame has to be bigger. Now, what do all these silly numbers mean? Here we go. The TS tells you, first off, 284 is the frame size. And frames range from 143 to 445. Not every number in between, but basically there's a range of them as you go along, with big gaps in there. Shaft center line is a little trick. You want to be real smart. If you've got a horizontal motor sitting there, the distance from the base or floor that's sitting on to the center of the shaft will be the first two numbers divided by 4. In other words, a 284 frame motor is 28, the first two digits. If you divide that by 4, you get 7, and that'll be the distance from the base it's sitting on to the center line of the shaft, 7 inches. The T means 1964 rewrite, and it hasn't changed since then. We're still using T-frame motors, okay? Prior to that, in 1952, there was a rewrite design, and it used U. So I can remember, I'm old enough to have sold U-frame motors. Then, prior to that, S. So today it's T, but at one time it was U, and even before that it was S. The S, the 284 TS, the S at the tail end, indicates, as I mentioned before, a short shaft design, not intended for belt or chain drive, applicable to all two motors at and above 30 horse. Below that, they don't throw in the S, but if you get it at and above 30 horse, then they do. You may find, basically, if you have a number beyond the T, or a letter beyond the T, if you have a C, it indicates a C flange, which is a male rabbit. In other words, the inside sticks out, for mounting on different types of equipment. Some sewage pumps come, if they're going to be motor driven, externally motor driven, have a base for that, whatever. D flange, same kind of idea, except it's a female. In other words, there's an indent on the flange for mounting. JP, as I mentioned before, has a special long shaft for close coupled pumps with packing. JM has a much shorter shaft for close coupled pumps with it. P indicates a P flange, which is a female rabbit, end mounting. It's P base that vertical turbine pumps use. That they're, in fact, they're very often referred to just simply as P base motors. Now, let's talk about vertical turbine pumps. You can get normal thrust, which some are used on sewage pumps, whatever. It's kind of rare nowadays. But the moment you say high thrust, now you're talking vertical turbine country because the pump has inherently, as we saw before, an awful lot of axial thrust downward. Okay, so the vertical turbine pumps are designed, or motors are designed to have that high thrust capability. And there's two different designs that you can get, either solid shaft or hollow shaft. A hollow shaft is primary intended vertical turbine in deep well applications, but a lot of municipalities use it. Come back to that. With smaller motors, say below 100, it's easier to adjust the pump shaft because it's about the right height. With say a 75 horse motor, you can reach over and you can adjust the shaft that's sticking through the hollow motor. And the discharge head can be built a little bit lower, so it's a bit stiffer. The solid shaft design is most common in industrial applications. And again, in the bigger motors, it's easier to adjust the pump shaft because it's under the motor, not on top, the adjustment, and has less shaft whip for mechanical seal, whatever, because it is a solid shaft. And you'll see how the hollow shaft is done. Hollow shafts can get a bit of whip in them, which mechanical seals don't like. So solid shaft is better with mechanical seals. They also can tolerate upthrust, and that can happen in a low head application or a booster pump application. If you get in a situation where it tries to turbine or whatever, it's not uncommon to get upthrust where the shaft is trying to poke up. And solid shafts don't care much about that. It's a big issue. Or if a shaft starts to unscrew. Upthrust is a problem with hollow shaft. Now here's what they actually look like. You can get ratchets that prevent the motor from spinning other than the direction that pumps typically do. But basically, these motors intended for deep well applications, and upthrust can be problematic. What I was going to say here can be problematic, particularly with solid state starters or adjustable speed drive applications. That's the one problem with the ratchets. The ratchets are noisy as they come off speed, and it's not doing them any good. So if you've got a soft start, you're going to hear it, particularly when you shut the motor down. You will hear that thing rattling away. And similarly with an adjustable speed drive, as the motor slows, you get noise. And you see the hollow shaft motor, how the shaft itself, bearings top and bottom, but it's actually hollow. So there's an extended shaft, head shaft as they call it, that extends from the pump shaft up to the very top, where there's an adjusting nut allowing you to ultimately adjust the impellers down below or compensate for shaft stretch and all that. And then there's a driven coupling piece. We'll get into that a little further on too. Submersible motors basically are designed based on conventional horizontal motors, but with customized shafts and enclosures by the manufacturer. The motor case can be dry or filled with oil. If it's filled with oil, the heat will transfer to the casing itself, which transfers into this, radiates out into the sewage wastewater and cools the thing. If you go dry, then basically they will flow liquid through a double wall casing and allow it to cool the casing. And of course the motor is up tight against that, so it will transfer the heat. Submersible well pump motors. There is a standardized design on the end of them, NEMA standard, and so motors are interchangeable, manufacturer to manufacturer, assuming they have either 4, 6, 8, or 10-inch bases. And what that means is a 4-inch motor will fit. It's a bit smaller than 4 inches. It's designed to fit within a 4-inch inside diameter well. or 6 or 8 or 10. One thing Franklin does with their submersible motors, they're potted. In other words, there's a combination of sand and silica that go into them. So they're actually potted, which is a good thing. A conventional motor on a variable speed drive, you will get sort of a halo current, which is not fatal but doesn't help the motor. Let's put it that way. It's there and you just live with it. Potted, that disappears completely. And Franklin has just come out with permanent magnet high efficiency motors up to 300 horse. Since most submersible wells essentially utilize vertical turbine bowl assemblies, at the bottom end of the submersible pump is a high capacity thrust bearing. In other words, the thrust of a vertical turbine is down and the motor is up high, so the thrust is pulling down on that motor. Here the motor is under the pump. The submersible motor is under the pump. So that's a compression force, again, forcing down. So the motor has to be able to tolerate that force down on it, which can be fairly high. So what it is, they have a high capacity thrust bearing at the bottom. It's a Kingsbury, in most cases, a Kingsbury plate type bearing using water as a lube. And here, much like car bearings, the actual engine bearings are not ball bearings in almost all. They're a metal sleeve with oil serving as the lubrication between them. Here, you have a smooth surface and a plate that's allowed to pivot a little bit to adjust. And it's almost like the plate is water skiing. That there's water allowed to go right down to the bottom. In fact, these motors are water filled. Excuse me. And those plates will actually form a small surface of water as it turns around. And that's what is actually doing the lubrication. And of course, because it's a fairly large area, they can tolerate a very high thrust. Now it says here, self-aligning Kingsbury, so that's why they're pivoting on it. Those, see those little ball things. There's the diaphragm to make sure that the pressure in the motor is the same outside the well. Casing, anti-track resin system. That's what we talk about. They're potted. It's a combination of sand and epoxy and all sorts of wonderful things up there. Service factor. Most open drip proof or weather protected one motors have a service factor of 1.15. And here's how NEMA actually defines service factor. The service factor of an alternating current AC motor is a multiplier which, when applied to the rated horsepower, indicates a permissible horsepower loading which may be carried under the conditions specified for the service factor. Voltage and frequency maintained at the values specified on the motor's nameplate. In other words, a little bit we're in paradise, but it is there. Now, a motor will be its most efficient operating at its rated horsepower. 100 horse motor at 100 horse. Therefore, applying any unnecessarily oversized motor is simply wasteful. We actually, from an efficiency point of view, want that motor to be operating pretty close to its rating. Conversely, overloading a motor can significantly shorten life. Ideally be sized with a basic rating that is at or slightly above the normal required operating load of a pump, and the service factor being at or above the maximum pump requirements, typically occurring should the pump ever operate at static head only. And basically that's how I would size a motor, so that you're at or slightly below rating over the normal operating range you anticipate. Then have the service factor. Hopefully that's enough to allow the motor to operate if you're at static head only. If it isn't, then you have to upsize the motor a bit. Submersible sewage pump motors, because they have better cooling, will often have a higher service factor than the manufacturers go, quite common 1.2. And like with submersible well pump motors, are designed to permit full utilization at service factor. In other words, a 100 horse motor with a number of manufacturers effectively is a 120 horse motor because they allow a continuous 1.2 service factor. And submersible motors, like Franklin's whatever, they're 1.15, and that's a continuous value, so you can run at 115 horse with a 100 horse motor forever and ever, amen. Voltage. They're generally motors intended to operate or designed to operate on a voltage slightly less than the rated line voltage. This is done on the assumption that you're losing power through conductors before you actually get at the motor. For example, line voltage 120, the motor will be typically rated 115. 208, the motor will be rated 200 in the States. In Canada, they rate them at that voltage, and I guess they assume the power transformers will be close. I don't know why we do it. Canada, we're a little weird. Anyway, 240 volt is 230 motor, 480 volt would be a 460 rated motor, and 600 volt would be a 575 rated motor. Now you know why the differences. And here's an interesting little thing about voltage games. At one time, three-phase U-frame motors were often rated 208, 220, 440. In other words, they could operate at either 240 or 480, depending how the windings were hooked up. And that's just a case of how you wire them into the junction box. Easily done. You parallel them, it's 240 volt, you run them in series 480. And conductor losses are assumed to be more than they were before. In other words, 240 instead of being 230 is 220. You see that. But the interesting thing is that 208 was so close to 220 that the motors were allowed to operate off a 208 power supply hooked up for 220, okay? But when 1964, when T-frame motors came out, the gap was too big. They upgraded the motor voltages and the gap was considered too big, so 208 or 200 became a separate voltage rating from 230, 460. But some motor manufacturers, Toshiba being the first that I'm aware of, were designed to again allow like a 200, 230, 460 rating, or 208, 230, 460 in Canada. They simply up-designed the motor slightly. Then you could use that motor with the three voltage ratings on any of the three voltages. You didn't have to have two separate motors in stock. Generators. And a generator, a genset, basically is an AC generator or alternator powered by an engine. The alternator is similar to an induction motor, except power is produced within the stator, and the rotor current is controlled by DC current applied externally, so through slip rings. So you're controlling the current and magnetism of the rotor to control voltage and everything else, basically voltage. And that's done by a DC power supply and the DC power, the whole big deal there. But that basically is what you're doing. It's by controlling the DC input through slip rings to the rotor, you can control the motor. Now we get more into mechanical. The preferred type of driver in most cases, diesel. Diesels offer reliable starting and a safe fuel supply. Spark ignition engines are inherently less reliable in terms of starting particularly, and the fuel is either quite flammable, gas or propane, or subject to loss in an emergency, like natural gas. If you're running off natural gas and in an earthquake, natural gas will be one of the first things to go. Can you power them off gas turbines? They're complicated to start and expensive to run. Yes, you can get a lot of power out of a very small unit. But as BC Hydro guy once told me, he said, you use them for emergencies and you only run them if you have to because they are expensive. Now, since the frequency of the power generated is a result of the number of alternator poles and the speed of the engine, most genset engines are governed to operate at 1800 RPM. There's the occasional at one time 3600 RPM, very small diesels. And if you get into larger sizes, really big stuff, then you're down to 1200 RPM. And maybe even lower. But basically, the vast majority, 1800 RPM. So there's your fundamentals of a generator. We'll get into how they're, as a genset, they're packaged in a bit here. Automatic transfer switch. Basically, you want to transfer the load from your utility to the generator in the event of a utility power loss, and then back again when utility power is restored. And for that, you need an automatic transfer switch, ATS. There's different ways of doing it, a couple of different ways. One is a motorized circuit breaker design, which basically they can either be thermomagnetic breakers or strictly disconnect breakers. Obviously, disconnect breaker is a little bit cheaper, but sometimes they believe in the actual thermomagnetic as a protection factor, okay? And there they have motorized. So fundamentally, when the thing goes to transfer, the power is dead on the line. If it goes to transfer over to emergency, There's a little motor power that will move it because you've got emergency supply. The generator has seen the power failure and start it. So you do have power there. So a little motor will drive the circuit breaker mechanism, disconnect offline, and then reconnect to the generator, bang, and away you go. And same thing coming out of it. You have to disconnect and then reconnect. And because of the fact of how you're powering it and you're worried about the motors out there, talking about generator, it takes a few seconds. So there's a delay between the two of them with the motorized. The other approach is to use a high-speed solenoid actuated switch design, and I'll show that in just a second. And I'll make the comment, basically, who's the man? Here, show you the drawing. Who's the manufacturer? I'll mention names. ASCO is by far the one that does this best. I've seen GE do it. We had problems with GE. Would I deal with them again? No. ASCO's always been very good with the switches. And in a lot of cases where, a few cases where I have allowed somebody else to bid afterwards, I wish I hadn't. How they actually work with ASCO. You can see right now there's a common connection, okay, in the center, and that's going to your load, your pump station, whatever, treatment plant, whatever, okay? And to the left, you can see it's connected, touching to where the normal power supply is, okay, fine and dandy. Now, when it decides, and we'll get to that in a minute, when it decides to flip over to emergency, you notice there's a big solenoid up top, and the core of that is connected with a lever to a weight, and you can kind of see how the mechanism works. What happens is, bang, they shoot power to that solenoid, which, slowing time down, will pull up the core. The link will cause the rotating weight to rotate to the left, and in doing so will cam the switch over the other direction. If you look on the right, then as soon as that core has come up, immediately they unpower it, and the spring on the core drives it down, so the link is now to the other side. And as you can see, you've flipped from normal source to emergency source, and it is super quick doing that. Okay. Also, much more compact than using motorized breakers. It doesn't have the overload things that circuit breakers would normally have, but your gen set should have a proper circuit breaker on output. Your power supply should have protection, etc. So you really don't need to have that protection built into the transfer switch. Now, how the normal sequence goes is like this. You can set them to what you want. This is what I use because it's easy to remember. You hold out your hand and you got a thumb, but you call it 5 fingers, okay? So what happens is, first off, the transfer switch, time delay engine start. It counts out 5 seconds. In other words, if the line power comes back within 5 seconds, it was a momentary blip. Don't worry about it. The power comes back on. Everybody's happy in a way. You probably got your equipment programmed so that after a power delay, it will automatically delay before it starts starting things back up. But in terms of the transfer switch, it doesn't do anything if the power restores itself within 5 seconds. If it doesn't, it will start the engine. Time delay engine start. Next, we're going to transfer from normal utility power to the emergency genset power. And again, another 5-second delay. That only happens after the genset is actually up and running. So the timing for the transfer doesn't happen until the emergency power is up. So time delay normal to emergency, time delay any, 5 seconds again. Now we're running on emergency power, okay? And it can last 5 minutes, it can last 5 hours, 5 days, whatever. When ordinary power comes back, we look at it and have another delay, time delay emergency to normal. While we waited before for the genset to come up, in this case, we're waiting, is the utility for real, or is it just come back a momentary blimp and then fallen right back out again? So we wait for 5 minutes. And you have to have 5 minutes of normal power there before we flip from emergency back to normal. And then we run the genset for 5 minutes without load to allow it to cool down. So there's your sequence, okay? A genset should be able to handle the load likely to be imposed upon it. Okay? Uh, and as a general rule, the genset kilowatt rating should be at least twice the size of the horsepower rating of the largest motor. I go a little more if it's a submersible well pump. So what you're saying is, okay, fine, I've got three 100 horse motors. So 300 kilowatt plus 50, which is double the horsepower kilowatt rating of one. Horsepower kilowatt are not equal. That compensates for safety factors. But basically speaking, that's how you would look at it. If I got three 100 horse motors, I would have 3.5 times a 350 kilowatt genset. That's kind of sloppy, but it does work very well. And if you spec at that, you're pretty safe. Okay. Solid state starters have proven to be sometimes problematic with gensets hunting. Not quite sure why, but they can be. I warn you that can happen. Adjustable speed, you may even want to oversize the genset a little bit. Adjustable speed drives don't seem to care very much about genset problems. They just don't have them. They work very well with generators, very well. Okay. Now, appurtenances, stuff you also need. Good sized battery. Diesel engines with a high compressor require a large starter motor with a high DC current draw. Therefore, you need a good size, reliable battery to get the thing going. Automatic charger. These things can sit a long time. So a smart automatic charger that will regulate charge to prevent overcharging is connected all the time. A jacket heater. Diesel engines do not like to start cold. So what you do is have a thermostatically controlled electric heater that ensures the engine coolant is maintained at a warm temperature. Not only greatly assess engine starting, realize the piston comes up on the diesel, the air is compressed, fuel is injected in. It's the temperature from compression and that high pressure allows the fuel to combust on its own, no spark plug. So the warmer the engine is, the better it's starting on the first turn. Okay. Also, having this electric heater will cut down on condensation within the engine and around the engine. Now, with gensets, enclosures, an open, as you see in the picture, intended to be installed within a room with provisions for air inlet and discharge and engine exhaust. Ideally, this is a separate room dedicated for genset use only. The success of that installation depends in the main on the abilities of the designer and contractor. How well is it designed? How good is the contractor? It can be a little fussy. Doghouse enclosures. Basically, the genset is designed for outdoor enclosure and installed within a doghouse, as they call it, which has service doors on the side, has all the stuff you need in it, and is sound attenuated. Installations are always simple and ideal for regions having a moderate climate, because you're going to be servicing in the wintertime just as well as in the summertime. Beware security issues with factory-built packages in unfenced locations. In other words, if you've got a vandal area, you don't want them near something like this. See the little cap on the top of the exhaust? Kids can climb up on top of it and drop gravel down that into the exhaust. Real easy, okay? Next step up, so you can get doghouse enclosures that are not done by the factory, that are custom built and are vandal proof. Walk-in enclosures. Let's take it a step further. The enclosure can be large enough that you can actually walk into it. Essentially, it's a prefabricated genset room. And any genset can be installed within a walk-in enclosure. This approach is advised certainly for anything over 1,000 up to at or over 1,000 kilowatt, and we're harsh winter climates. You can have it nice and toasty and warm inside, and away you go. Roadable units. Basically, they're usually doghouse enclosure on a trailer doghouse. You're not so much worried about vandals because you can park this thing in a secure location. And they can be moved site to site. And so you can, I remember one municipality basically through their SCADA system, they were able to tell what the wet well levels were. So they would basically have somebody, a pickup truck or whatever with the genset on the back. They'd go to the one that's got the highest level, closing in on overflow, pump that thing right down, and then go to the next one that's next highest and move themselves around. Bit of a pain, but it saves money. Also, You can store it where there's utility power, so the automatic battery charger and jacket heater are there. And shared warning, electric utility, touching wires causes instant death, $200 fine. Breaker box, do not touch. Not only will this kill you, it'll hurt the whole time you're dying. And this is a picture of Nikola Tesla sitting there in a chair while a bunch of very high voltage sparks, none current, are floating around. And that's it, and I hope you did enjoy.